This conference will now be recorded.
Okay, fine. So, in the last session, we started talking about functions. Now, why did we require to understand functions? Because functions talk about explanatory variables. Functions talk about response variables or dependent variables, and above all, they talk about the concept of causality. It helps us understand the causality between two variables. Now, this is again something that we need to understand in risk, because whatever type of risk we are trying to model, be it market risk or be it credit risk, right? We require to understand this framework. So, we understand to identify the key risk drivers. We need to understand the core. Uh, we need to understand, the core framework. We need to understand the core factors which are affecting or creating the risk. So, the entire idea of risk models is to identify risk drivers, and hence we need to understand causality. So that's one part. Now, the next thing that we again talked about over here was the concept of a limit of a function, right? And another important thing that we said is that we over here in mathematics we talk about basic functions, but when we talk about market risk, the type of functions that we would be talking about mostly would be stochastic functions, right? Functions with a white noise or an error term or a stochastic component involved into it, right? So we talked about concepts like the domain of a function, the codomain of a function, and so on. Now, after this, the next thing that we talked about was the two basic type of functions that we would require every time, day in, day out. That is, one was the exponential function, the other was the logarithmic function. So we just introduced these functions because exponential transformation and logarithmic transformation are the two most common transformation that we generally go through when a model, so when variables are being transformed, right? So over here, when we talk about, so basically these are the two functions which were introduced. The next function that we talked about over, the next thing that we talked about over here was the concept of a limit of a function, right? Now the limit of a function, as we said, is very important to explore discontinuities in their behavior, right? So basically, so if x is tending to 2, what value is the function fx tending to? So it gives us a limiting value or a kind of a limit where this particular function may converge to. Now, from limits, what we derived out was the concept of continuity, right? So what was continuity? Continuity would be a function. So basically a function would be continuous at a point if the left hand side limit, right hand side limit, and the limit themselves over there was equal, right? So that's what continuity is. Right? So that is what was continuity. Now, when I talk about continuity, so these are the three basic pillars of classical calculus, right? So these three together, right, cannot take you too much. They are the three basic pillars of understanding market risk or any kind of risk. Now, after this, from here, we'll introduce the most important concept, right, on which calculus and on which any kind of dynamic uh, subject stands or dynamic finance stands, right? So that's the concept of derivatives. Now, this derivatives is the core, is the crux of any risk model. So, we talk about different modeling methods and all, but what we simply do or we try to interpret is the derivative. So over here, we need to understand what is derivatives. So basically, when I talk about the derivative over here, I'm talking about the derivative of a function. I'm not talking about the asset derivative, right? So let's try to understand this function from, let's try to understand the concept of derivative first. So What do I mean by the derivative of a function? And why do I need it in understanding any kind of risk? Right, derivative. Derivative. So what is this derivative all about? What is this derivative of a function all about? So derivative very simply tells me that what is the change in y if x was to change by 1 unit. So what is the change in y the change in y if x was to change by 1 unit. If x was to change by 1 unit. So derivative is actually the measure of causality between x and y. So it shows that if x as a variable was to change by 1 unit, what would be the corresponding change in y? And that is what precisely is derivative. So derivative does what? It helps you capture the element of causality. So let's try and understand the concept of derivative from the graphical perspective. Right. So this is the measure of causality. This is the measure of causality, right? Now, when I say that this is a measure of causality, so what do I mean? So let's see graphically how this part works out, right? So let's say I have this graph over here, which is the x and the y, right? So I have say 0 over here. So this is my origin, right? Over here I have my xt, and over here what I have is my yt, right? So over here yt equals to f of xt, right? So over here what we have is, so between 0 and xt, so this is xt, and over there I have yt, right? Now let's say I have a function and I draw the function like this, right? Now I want to know what is the derivative of x, or what is the derivative of y at x0. Let's say this is x0, right? So it means that over here, x0 corresponding to x0, y0 will have a particular value, right? So what is y will have a particular value which is y0, right? So now if I ask you that what is the derivative of y at x equal to x0, so it means that if I change or if I increase x by 1 unit, what would be the impact or what would be the marginal impact on y? So if everything else remaining unchanged, only x changes from x0 to x0 plus delta, then what would be the marginal impact on y? So this marginal impact is nothing but the causality between variables. Let's say I am giving a loan to a particular borrower, right? And I ask the question that there are two scores: the internal score, which is designed by the bank, and there is the bureau score, which is extracted from the bureau. What would be the impact on the dependent variable y if x was to change by 1 unit, or if the internal score was to change by 1 unit, everything else remaining unchanged? So derivative is, so this is captured by the derivative, or in models the regression coefficients to the regressions that we observe, right? So this is precisely what derivative means. Derivative helps us capture the marginal impact of a change in an independent variable on the dependent variable, right? So it says that if x was to increase by 1 unit or increase or decrease by 1 unit, what would be the corresponding impact on y0, right? So this is the reason why derivative, because derivative of a function captures its, the marginal impact of a change in the independent variable on the dependent variable. Therefore, derivative is very important. So let's say I say that, okay, x has been changed from x0 to x0 plus delta. So this is the impact of, this is the increase in x. Now what would be the corresponding impact? What would be the corresponding impact of y on x, right? So this is where the next question comes in. So basically what we want to know is that if x was to increase by change by 1 unit, what would be the corresponding impact of y? Because when x changed by delta units, y changed by something, some amount to y dashed. So what is the increase in y if x was to change by one single unit, right? And this is where derivative comes up. So how do you find out derivative? Let's say, so over here I have a function, right? A function, let's say y equals to fx, right? So this is a basic function. So this is any function, right? Now what happens is x increases from x to, so x was initially defined at x0. So this meant that at x equal to x0, y had the value y0. Now x0 increases by an amount of delta. So this is your initial value of y. So this is the initial value. This is the initial value, right? Right. The next part is, now what happens is x changes to x1. Right? So now, how does x move from x2 to x0 to x1? That is by increasing by delta. So over here, what we have is, so y1 equals to f of x0 plus delta, right? So this is your final value. So over here, the first question that comes out is that what is the total change in y which has been observed. So now say, so it is x0 plus delta. So this is the final value of y minus the initial value of y, which is f of x0. So this gives you what? So this gives you the total change that you observe in the dependent variable. So let's say like this, that y is so the equation is y equals to x, right? So if the equation y equal to x, when x is equal to 1, y is 1. When x changes to 2, let's say x increases by 2 units, then so then x becomes 3, so y also becomes 3, right? So the total change in y is what? Initial final value of y, which is 3, minus the initial value of y, which is 1. So 3 minus 1, 2 units. So when x has changed by 2 units, y has also changed by 2 units, right? So this is where delta y comes in. So delta y shows the total change in y due to the change in x. Okay. So the next part is, so now the question that comes out is that what would be the change in y if x changed by 1 unit? So over here you can see that the change in x has been delta, right? Or let's say delta x. So what I say over here is that when x changed by the amount delta x, the change in y was delta y. So when x changed by 1 unit, the change in y with respect to 1 unit change in x is delta y divided by delta x, right? So what you get to see is this thing, f of x0 plus delta x minus f of x0. So this is the final value. So this is the total change in y that you could see divided by the total change in x. So this figure shows me what? So this shows me the total change in x due to 1 unit, total change in y or the dependent variable due to 1 unit change in x. So if x was to change by 1 single unit, what would be the corresponding responsiveness on the dependent variable y, right? Now over here, one thing that we need to see is that when I talk about delta y, delta x, I'm talking about some arbitrary change. Now this change can actually be very small, because when we consider financial instruments and when we consider financial assets, we talk about their returns in a continuous frame, right? So I talk about the return series being generated being in the interval of minus infinity to plus infinity. So what is the fact, what is the change in y if x, what is the change in the demand of the or what is the change in the asset value if the return on the asset changes this much? What is the change in the fundamental value if the rate of return on the asset changes by this much? And this change can be in any small numbers, right? Because this is a continuous variable. So in market risk, we deal with most of the variables which are continuous in nature. So that is why, so that is the reason why over here so over here we need to consider this function for very small changes in x. So if over here we see that, so if the change in x is actually happens by very small amounts, so it is delta x tends to 0. Delta y, delta x, which we call our first order derivative, that is dy dx. So your dy dx is nothing but limit delta x tends to 0, and then what you have is your f x0 plus delta x minus fx divided by delta x. And this version is called your derivative. So your derivative is nothing but it records the change in the dependent variable when your independent variable changes by very small units. So due to very small change in x, what would be the corresponding change in y? And this responsiveness, so therefore derivative is a measure of responsiveness of one variable on the other, right? And that is what we also called the causality coefficients, right? Derivative of a derivative is a measure of responsiveness. Is a measure of responsiveness, right? So is this concept clear? Just go through this concept, whatever we have discussed, right? And then we can take it up. Because derivative is going to be a very critical concept when we move into the market risk side. Because one challenge with market risk modeling is that, like in credit risk, you need not understand the core theory behind credit risk. It has more of you can just run the codes, or you look into okay IVWOE and stepwise you develop the model. But for market risk, you cannot do that. You have to understand what goes behind, because without understanding how derivative is valued, you cannot understand how is the risk arising from there. So you need to understand the basics of the theorems, right? So even if you don't need to go into the details of it, you need to understand how it actually works, because that's a very critical part. This is a very quantitative module. Hence, these concepts are very critical over here. Tom, Umesh, just go through it. Just check if there are any queries. Right? Fine. Okay. Okay, fine. Now the next part that we'll talk about is one of the again, it's another one of the most critical portions that we need to talk about, or that we should talk about, that is optimizing a given function, right? So when I talk about optimizing a given function, or so after we have talked about derivatives, right? So the next big thing, or the next most important thing that we talk about is optimization. Now, when I optimize a given function, what do I mean by that? Now, optimizing or means to reach out to a point where the function has reached its peak or has reached a trough. So, optimization broadly are of two types. The first type is obviously maximum, or the maxima of a function. The second that we have is the minima of a function. So over here we have two portions. One is maxima, and the next part that we have over here is the minima. maxima and the minima, right? So these are the two parts. Now in both of these, so obviously yes, we need to optimize, right? So whenever we are in kind of a risk modeling module, or whenever we are into risk or risk model development or stuff like that, we are trying to talk about maxima. So we are trying to either maximize something or minimize something. So there is always an optimization algorithm which is going around it, right? So this is what we need to understand, right? So over here, when I talk about maxima, so obviously, so if I want to maximize or minimize a function, right? So that is where the all these four pillars, function, limits, continuity, and differentiability comes in together. So I need to understand the limits, continuity, differentiability. Limits, continuity, and differentiability. So So this is where the function. So this is where we need to understand how to maximize a function. So basically, let's say I'm trying to choose any particular. I'm trying to make a choice, right? Let's say I'm trying to make out whether, so how much of investments, or how much should I invest, because every time I invest into it, into an asset, right, I'm increasing my returns, as well as at the same time what I'm doing is I'm increasing my RWA as well, my risk weighted assets as well. So I need to reach a kind of a optimum where the difference between the two, so where a where a sweet spot between the two is struck. So that is where the concept of optimization comes in. So initially, we'll first start off with the concepts of single variable optimization, right, of single variable functions, and then we'll graduate to understand the multivariate functions, the multivariate optimization exercise as well. So over here we have single variable functions. Single variable functions. So for the single variable functions, we are trying to do the maximization and the minimization, right? And then we'll gradually move to talk about the multivariate functions. We'll talk about the multivariate functions. So multivariate functions, right? So these are the two important things that we have, right? So let's start by trying to understand what is a maximum and what is a minimum. These two concepts are very basic and we all know them. Our objective over here would be just to kind of formalize that, right? So once we can formalize it, then we are more or less in a comfortable position. So let's start by drawing the graph. So let's start by drawing a small graph over here. Right, so x. Okay, so let's say I have a function like this. So this is a function, right? So one thing we can clearly say is that this is a part where the function has been maximized. After that, the function has fallen down. And this is the part where the function reaches its minimum. And from there, it again increases, right? So if you put a line through this, right? Or if you put a line through this, what we'll see is that, so what happens in this maximum and minimum? So first of all, let's trace this function. The function x is y is increasing as x is increasing, right? So the rate of increase of x over here is greater than 0, and then it reaches a point where it stops, right? So the point where it stops is the point after which it cannot go. Hey, hi guys. Yes, am I audible now? Okay, so there's a bit of a connectivity issue. Just give me a couple of minutes. Just let this whiteboard connect to the server. So there's a kind of a connectivity issue. We'll just get started in a couple of minutes. Just give me 2 minutes, 2 to 3 minutes time. Okay, so okay, just to resume back things. Okay, So over here, so as I was saying, so if you have a look into this part, right, in this, so if you have a look into the function from this part, right, so on the right hand side and on the left hand side, right, so you see that the function increases over here. So as x increases, y also increases up to a point and it stabilizes there. So after this point, the function cannot increase. If you want to increase your function, if you want to increase the function value by increasing x, it starts falling down, right? So this is where this flow actually happens, right? So over here, what you can see is that x is increasing, y is increasing, and as y is increasing, y increases and reaches the top, and then it falls down. So now let's have a look into this behavior. So over here, when we have done this part, right? So how do I identify where a function maximizes? To understand where the function maximizes, I need to understand the characteristics of the function at the point where it is reaching a maximum. So what is the characteristic? So before the function is reaching a maximum, what is happening? The function is increasing by x, right? Hello, am I audible now? I think I'm audible now, right? Perfect. Okay. So over here, as x is increasing, y is increasing. So it means that the change in y with respect to a unit change in x is greater than 0. So over here, the function, the independent variable increases with an increase in x. It means what? The function is still not saturated. The point where it reaches its saturation, right? What happens? The function y will stop increasing when it reaches to x. So this is dy dx is equal to 0. So that means at the peak point, the function stops, right? So the function does not increase. So now over here, what happens that as x increases, y starts decreasing. So it means that the function over here, the change in y with respect to change in x is negative. So what happens over here? So the first thing that happens when a function is maximizing itself, it reaches up. So first of all, a maximum is nothing but a point of optimum. So when it becomes optimum, the change in y with respect to the change in x equals 0, right? Now, what is the next thing? Now the next thing is the slope changes from being positive to negative. It means that if with every increase in x, right, the slope itself becomes negative. The slope gradually decreases. So it means that With every unit increase in x, dy dx becomes negative, that is less than 0. So these are the two conditions which is required for the function to reach, for any function to reach a point of maximum. So what are the two criteria which are required over here? The first criteria for maximization is that the function must become invariant with respect to changes in x. So that is dy dx is equal to 0. The second is d2y, that is the second order of the derivative, must be negative. What it means is that if your function has reached a maximum, right? Now, after that point onwards, every time you increase x, the slope of the function should go down. So this is where your maximization principle comes into play, right? So I'll say that a function fx reaches its maximum if or when the first order derivative is 0 and the second order derivative is less than 0. So this is precisely what the concept of maximum is, right? So similarly, you can just think about it on the other side. So how would a minimization of a function look like? So over here, first of all, what would happen is that the function would start falling, right? And it would reach an optimum, a minimum. So when the function reaches the minimum point, then again dy dx will be equal to 0. So dy dx is equal to 0, right? Now if a function has reached its minimum, it cannot go down any further. And now if you want to increase x anymore, the functional value will rise. So only the functional value rises after reaching a point will you say that it is minimum, right? So therefore, the second order condition over here for minimum of a function is d2y dx2 is greater than 0, right? So now the question can come out that why did we use the second order condition? Now we are using the second order condition to know the direction in which the y will move after it hits that optimum point. Now I will say that I am at a maximum point if y falls from that point onward. So y cannot reach after, cannot go beyond that point. Similarly, I will say that I am at a minimum if y cannot go below that point on further increases of x. So basically, the second order condition tells me that when you increase x by 1 unit any further after the point of optimum, then what happens to the slope of the function? So if your slope of the function increases, right, after it hits the optimum, right, it means what? That the optimum is a minimum. I cannot go below that. So I have reached the minimum, I have reached the trough. Now I can only go upwards, right? So if the second order is greater than 0, you know that the function is a minimum. Now, if the function is a maximum, what will happen? The function has reached its peak, right? Now, how do I know that that peak is a maximum? I know that that peak is a maximum if the function cannot go any point after that. What happens is after that point, it slides down. So then, with any increases in x, the function, the slope becomes negative. That is, d2y dx2 becomes less than 0. right? So is this idea clear, Umesh, Tom? So the first order condition, right, when we look into it, gives us an idea of an optimum. Now the second order condition actually tells me that whether the function that I have used created, whether it is an optimum, whether that optimum is a maximum or a minimum, right? Okay, fine. So this is what the basics of the first, the univariate calculus is, right? So now one thing, just remember one thing, that if a function is differentiable in nature, right, then it has to be continuous. Right? On the other hand, if a function is continuous, then it does not always mean that it is differentiable in nature. A function is differentiable if it changes gradually and smoothly in a smooth manner. But if that changes, or if that changes, or if the change happens very abruptly, such that it is kinked in nature, so there are certain sharp edges or certain kinks in the function, then you know that that function is uh, immaterial. I mean, that's a non-differentiable function, right? Even if it is continuous. So basically, the maximum, minimum can be computed on differentiable functions which are continuous in nature, right? Okay. So now, after this has been done, like after the maximum, minimum, and functional limits, quantum differentiability is done. Uh, let's try to understand. Let's try to. So the next thing that we'll talk about over here is about So we'll talk just about some kind of yeah. So after this, so next thing that we'll talk about is dynamics, right? So how is it using these basic concepts can you identify the dynamics associated with equations, right? So how can you identify dynamic equation? How can you explore? How can you show that, okay, explore the dynamics over which a variable evolves, right? So this is something that we kind of need to know. But this is something that we will be talking about, right? So over here, so to understand the dynamics and how a variable evolves, how the path of a variable moves, the dynamics of a variable, right? We need to understand the concept of a differential equation. A differential equation and a difference equation. Because over here we will be dealing with both type of equations. One is a difference equation, and the next is the differential equation. Differential equation, right? So these are the two important things that we need to understand over here, so that we can explain the dynamics, the price dynamics, price path, pricing of asset derivatives, and so on. Right. So we'll start off with these two concepts. So before I start off with these two concepts, right? So just take 4-5 minutes time, just go through this, check whether you have any queries or not. Then we'll just take it up, right? So I'll just take a 5 minutes break and we'll get started around 5 2025, right? 5:25, around 5:25, 5:30, we'll get started again. So in 5-10 minutes time, we'll get started again. So just go through this, see if you have any queries, and then we'll start off with difference and differential equations, right? Thank you. So just go through this and we'll get started after.
This conference will now be recorded.
Okay. So functional limits, continuity, differentiability, and the basic concept of maximum minimum clear to us? Great. Now, the entire idea behind doing all these things, you know, or behind entire calculus is to study the movement of variables over a span of time, right? And that is where the role of difference and differential equation is required. Okay. So Umesh, it might be that Tom had dropped off because of his connectivity issues. So once he's sorted around that, he'll be back. So let's continue, and he can look into the recordings. Okay, fine. So, okay, so basically the the entire concept of calculus and all has been done to understand the dynamics, to understand the movement of variables across time, right? So to understand how is it that a variable's path is evolving with a period of time. And now when I talk about time, time has been defined in two distinct frameworks. One is discrete time, the other is your continuous time. So when I talk about discrete time, I mean, or I am referring to, say, discrete points in time, like t equals to 1, t equals to 2, t equal to 3, like this. So let's say the gap of every month. So where the value of this month or this variable impacts the value of the variable in the next month. So like this. So that is what we call discrete time. Continuous time is where the the output or the outcome has impacts in continuous time frame. Let's say, for example, uh, certain changes in interest rates will impact the money market or the financial markets in a differential manner or in a continuous manner, whereas it will affect the product market in discrete time. So basically, if interest rates are increased this month, right, in the first quarter, to get the first output, the impact on output is required the next quarter, right? So changes in interest rate last quarter will impact the output this quarter, but changes in the interest rates will cause immediate impact on on foreign institutional investments, right? So investors will immediately draw out funds or pull in funds into the economy just at the click of a button. So that's in a continuous time frame. On the other hand, so basically, when we try to assess the movement of variables over time, we look into time from two different aspects. One is discrete time, and the other is continuous time, right? So, and with this, there are two sets of equations or two different types of equations or two equation frameworks which help us assess the dynamics of variables in continuous time as well as in discrete time. So the first is your discrete time variable, so which is so the discrete time is also when we try to assess the dynamics of variable in discrete time, we call it the difference equations. And when we try to do it in continuous time, we call it differential equations. So this is precisely what the framework is, right? Okay, so let's think about it like this. So when I talk about time, time, right? So time is broadly of two types. Discrete time so first is discrete time and the second is the continuous time, right? Now to assess the dynamics of variable in the discrete time, we have difference equations. Difference equations, right? Now when I talk about difference equations, so how do they work? So it says yt is equal to say yt minus 1 plus zero point 0.2 yt minus 2 and so on, right? So this is what a difference equation is. So a difference equation shows that so yt is explained as a function of its own lags. So you are saying that so the way yt would evolve. So how would yt evolve? Or let's say, let's not put it like this. Let's write something like this with yt, right? So let's write 70 plus 0.56 yt minus 1, right? So it's 70 plus 0.56 yt minus 1. Now when you are doing this, what is the challenge that you have over here? right? So over here, one thing that you can see is that if you let's say, let's put a more easier form. So it's yt minus 1, right? So now over here you can see that if I subtract yt minus 1 from yt, what I'll get is yt minus yt minus 1 is equal to 70. That is delta yt is equal to 70, right? So over here, so this delta yt is nothing but, so delta yt is the, so this is what we call the dynamics of the variable yt. So what is the change in yt? So it says that the change in yt is always constant. So this is a typical kind of a difference equation, right? Where time is very discrete in nature. So time is equal to 1, 2, 3, like this up to k, right? Right, so differential equation. So now when I talk about differential equation, so how does differential equation differ from this? So y over here does not change in a discrete manner as it changes over there, right? So what I say is that, okay, my y changes continuously and I map this, or I try to figure out the change in my variable y by using this percentage change in y. By a continuous percentage change of y, I'm trying to figure out the change or the dynamics of y. So it is the percentage change in y. So if you see that this dy by y, it represents a continuous change where y itself is a continuous variable. So this reflects a continuous change in the variable. This reflects a continuous change in the variable. Yes, I'll just okay. So before I move on, I'll just explain this once again, and I'll move on. Right? Let's say so y is a variable, right? Y is a continuous variable for me. This y over here is a continuous variable. So it is. You can take any value between minus infinity to plus infinity. Right? So y belongs to minus infinity to plus infinity. Now y changes continuously over a period of time. So over here, if you look at the numerator, Umesh, it's but the change in y divided by the value of y. So the change divided by the initial value of y is nothing but the percentage change in y. So when I write dy by y, What I mean is it's the percentage change in y over a period of time, right? So when I want to find this change out, this is where a differential equation comes into play, right? So this percentage change in y, or this dy by y, is some function of the variable y itself. So it is, this y is some function of y, and it would be some function of some other parameter or some other external parameters. But when I solve this differential equation, or whenever I solve this difference equation, I'll not get a single value of y. Rather, I will get a locus, or a function which gives me a path that this value y would actually tread, right? So over here, what I have is this particular path of y, right? So if I solve this, this will give me locus of the variable y, right? Or a path of variable y. And hence, this is called a dynamic differential equation, right? So now there are multiple differential equations. There would be different kinds of differential equations and difference equations involved in. And so the next thing that we'll talk about is how do we solve a difference or a differential equation, right? So so Umesh, let's stop here for the day because Tom is also dropped off. So let's start with the difference and the differential equation, the solutions of them, and then to see how, where is it that these differential equations would be used in market risk, and how do we relate, and why is it important to know this for assessing market risk going forward, right? So let's take it up in the next class, right? So thank you, Umesh. Thank you for your time. Thank you for getting up so early in the morning and taking the sessions. So thank you for that. Thank you for your all your efforts. And let's get done. Let's get going next week. Thank you. Bye bye. See ya.